Hi everyone, we are back and we are going to deal with propagation of air, specifically dealing with bias air, and then we're going to do ANOVA analysis in this lecture. So previously we said the total uncertainty of any measurand x is going to be equal to the square root of precision air squared plus my bias air in that measurand squared. Now you're all masters of precision air, and we approximated that our mu is going to be mu is approximately x bar plus or minus t alpha over 2, comma nu, sx over square root of n, where x, again, is that measurand that of distribution or dispersion of the mean, standard deviation of the means, excuse me, to be very correct. But so essentially, this plus or minus, that precision error is just this. So that is your precision error. So we know how to deal with that. You know how to find those values and calculate that. But we haven't really touched on bias. We said that bias could be, again, this kind of value that's somehow related to resolution. But the other thing we haven't really talked about is, well, okay, I can kind of figure out bias from like the offset of a scale or a calibration error. But what happens, for example, what happens when I have to calculate something like this? Because oftentimes I'm measuring something and it's a function of other variables. So if I want to measure the volume of a cylinder, it's a function of a variable r and a variable L. And ostensibly, I'm going to take multiple measurements of that variable r, multiple measurements of that variable L, potentially multiple measurements of V. And how do I propagate essentially these errors? How do I look at and determine essentially the total uncertainty of that measurement? Because there's going to be some uncertainty associated with both those measurements. And depending if I'm using the same tool or a different tool, I have to build that into my analysis. So let's go ahead and figure out how do we actually do that. Well, we're going to propagate that uncertainty. So basically one equation of a standard deviation, if we have basically this linear function y of several independent variables, x sub I, each of which with some standard deviation, the total standard deviation of y would be given by this expression. Now, what we can do is we can do first order Taylor expansion. And if we want to estimate, so for example, let's say we wanted the total bias uncertainty, u sub y, and to estimate this, we're just going to kind of assume and basically do this first order Taylor expansion. And what we're going to get is a very similar expression. But now, instead of the standard deviation, we're going to assume that there is some bias uncertainty u sub 1 that's specific to each variable. So this is going to be the expression that we're going to use to calculate that bias uncertainty. We're going to build in precision if it's there, and then we're going to propagate that uncertainty. So let's take our first example. Volume of a cylinder. Tube of circular cross-section, nominal length of this and this, radius of this, determine the uncertainty in the volume. Now, when you read something like this, we need to kind of determine, do we have bias error? Do we have precision error? What's my fundamental equation? So first step is, what's my fundamental equation? So tube, circular cross-section, it's a function of length, and my radius, it's a volume of a cylinder. So my function is V, my measurand is V, and it's a function of radius and a length, and it's equal to pi r squared L. So this is my fundamental expression right here. Love it. Don't forget about it. We need to see, is there bias error, is there precision error? If there's precision error in V, or precision error in R and L, one of the things that we need is our T alpha over 2, nu, S of X over square root of N. Do you see anywhere here where you're told the number of measurements of the radius, the length, or volume? Do you see anywhere where there's the standard deviation information? No, we don't see that here. So there's no precision error here. So we can't calculate this. Now, that doesn't mean we can't continue on with our analysis, because for bias, do we know the tool? Are we given basically a resolution limit, right? Are we given a plus or minus? We are given a plus or minus here. So how can we break this down? Well, if I'm looking at here, I have two variables, radius and length. So my uncertainty in R is equal to, over here, my radius, 0.1 meters. Units are important here. Learn it, love it. Uncertainty in length is 0.5 meters. So now I can take these partial derivatives. So if I want the bias here in volume, it's going to be equal to the square root partial derivative of volume with respect to r, uncertainty in r squared, plus partial derivative of v with respect to L, uncertainty in L. Oops. Uncertainty in L squared. The units here, if I do, I'll do quickly that differentiation, 2 pi RL times a meter. So meter cubed squared. Here, dVdL is just pi r squared times another meter, so meter cubed. So in this instance, if we just plug and chug and calculate, and then we'll substitute in for r and L the nominal values, we're going to get something in units of meter cubed. So the bias error will be in that value. Now, there are going to be certain times. So, for example, let's say if I'm dealing with stress, force per unit area, that's going to be in newtons per meter squared, right? So I could have some uncertainty in force, which is in newtons, some uncertainty in area. And if there's precision error too, that's going to throw a wrench into everything. So sometimes you want to basically create this as a ratio. So you could just divide out by this and create a dimensionless, basically number, a percentage, a ratio. Something you might want to kind of get into practice because typically when you're dealing with a lot of these calculations, and even in this particular problem, because if you had precision error in R, that's going to be in units of meters. You'd have to, when you do the final calculations for uncertainty and volume, you're going to have to do bias error squared plus precision error squared, and then you'd have units that aren't mixing, and you'll see how that throws a wrench in it. So sometimes it's good to kind of just divide out here. So after that, you can just calculate, and we can see if we get essentially that same answer. Precision error in L and R 0. I'm going to actually go into here. I'm going to change. Go to 100 here, and then let's go ahead. So I can define my function. I'm defining essentially those variables. I'm doing exactly what we're saying. This would be the value in meter squared. You see I'm just plugging in for uncertainty in R, L, etc. But I might want to divide out, leave it in a ratio. This would give me essentially that bias error in percent, so it'd be 1.6%. But if I actually take and calculate the nominal value here I'm just plugging in for, kind of all the known values. And if I multiply this V times my ratio here, you see I'm going to get this 589, and that will just be the same as this divided by this should be 0.016. Beautiful. So you see, you can offer it another way. So this is, again, if I have to multiply this by 100, if I want percent, but you can kind of see the picture. If you want to, you can kind of just take that extra step, leave it in a ratio. If you need a number, and eventually you do need a number because you want an error bar plot, you can do it that way in order to get that final value. But this is a very attractive way to work with and solve these problems. So I would typically always put this in essentially in a ratio. And you can see how important it is in the next problem. So uniaxial tension test. Trying to measure stress in a rectangular block of aluminum. Experiment 14 times, blah, 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 blah. Measure the length of block, width, et cetera, et cetera. So what do we do in this problem? First step, what's our fundamental equation? Uniaxial stress, rectangular block of aluminum. We know that stress is equal to force per cross-sectional area. Now, is my stress a function of F over A? Are we given area? No, we're given length and width. So actually, we need to go do one more step. Force over length times width. So my stress equation is a function of F, L, and W. Is there any precision error? So what do we need for precision error? Number of experiments, standard deviation. I repeat the experiment 14 times. Force exhibits a mean of this and a standard deviation of this. So I do have some precision error in force, and that's going to be equal to, I'm not given any information, so I'm going to assume a 95% confidence interval. So T alpha over 2 nu, where my alpha in this problem is going to be equal to 0.05, 95%. My nu is going to be equal to, my number of force measurements is equal to 14, so my nu is equal to 14 minus 1, times the standard deviation of force, which is given right here. Hopefully, assuming those newtons are newtons, divided by square root of n. Measure the length of the block and the width. And I'm given both of those values as well. length of the block and width 14 times. So there's also precision error in width, and there's some precision error in length as well. What are these units? This is in newtons, this is in meters, this is in meters. How are we going to deal with this? I need to make this non-dimensional. So I need to divide out by x bar f, the average force value, to make sure it's newtons over newtons and is a ratio. So I need to take each of these and basically make that a dimensionless number. What about the bias error? Do we have bias error? And where? Let's see what we're given. I measured the length and width with a micrometer. So I'm told what the tool was. So I can say that there's some uncertainty in the width, which is equal to the uncertainty of length, which is going to be equal to 1 times 10 to the minus 6, assuming my micrometer could read a micrometer. I'm also told the force applied is plus or minus 1 Newton, so there's some uncertainty in the force that is 1 Newton. So I have precision error everywhere. I've got bias error everywhere. So now let's go ahead and let's solve this problem. So I'm going to go ahead. I'm essentially here. I'm actually calculating it explicitly. But you could just also calculate the same thing with your values. So I've got the means, I got the standard deviations, and you can see here, and actually we can do, we can double check, quantile, student distribution, length, actually it's just 13, degrees of freedom, comma, 1 minus 0.05 divided by 2. 95% confidence interval, 2.16, 2.16, fantastic. You see here, T alpha over 2, standard deviation over square root of n, and then divided by those mean values. So again, this is just a ratio as well. We can also define our stress values. Here you can see we're just getting our bias error. Now we're just plugging in for those uncertainties. 1 times 10 to the minus 6, 1 times 10 to the minus 6, 1. Plugging in for the nominal values. And finally, we can plug in for everything, and we get that uncertainty, which is actually times 100, so 7.9%. Now, this is not just a calculation exercise. What's the utility of this? Well, which is what uncertainty dominates? So actually, I'm gonna put my B stress. Let me grab this value. I'm gonna put it up here. So what is the largest uncertainty in this experiment? Most of the times you'll find that the bias error dominates, but in this problem, actually, it's the width. Now, why is that? Well, there's probably a large standard deviation essentially where that rectangular block that you got from a manufacturer. That's an issue. That's something that's hard to fix. Let's say, for example, I used a ruler, so -3, to make these measurements. In that instance, actually, I'm still, what if I do -2? You see here, if I use a ruler with basically centimeter tick marks, now what's dominating? That bias error. Now, I could improve that simply by just changing my tool. It's really hard to fix this uncertainty here. You're probably going to have to do more measurements, and you are going to hope that standard deviation doesn't grow as your number of measurements grows as well. So this is essentially how you want to propagate error, and it's a really useful tool. Again, basically you want to do this before you actually design experiments so you can kind of see what's feasible. So it's a really good activity to do prior to even buying and developing, experimental apparatus and experimental system. Fantastic. And all right, that's pretty much it for propagation of error. We'll see you next time on ANOVA, which is a fantastic and fun analysis, and then really fun to do in Mathematica to combine a lot of things that we want to do. So see you next time. Thanks. Bye.